from Lu?
No, Xing.
No.
Xing Peng.
Sorry. Talking to us about monochromatic short-term arithmetic progressions in ZM.
All right. First, I'm going to thank the organizer for giving me a chance to speak here. This is my joint work with my advisor, Professor Lu. He's over there. Okay, first let's start with some definitions. A k-term arithmetic progressions in integers is a sequence of integers in this kind of form. Here, a and b are some integers. For example, this 5, 8, 11, 14. This 4-term arithmetic progression. Through this talk, I will say KAP means k-term arithmetic progression. And here, in this k-term APs, A is called the initial term, and D is the common difference. And we already know a k-term AP is totally determined by the initial term and the common difference. If, in our talk, we allow B equals 0. That means all terms are the same. That's the generated one. We allow these kind of things. Now here, to coloring of the this notation means the collection of the first n positive integers. To coloring of this means give me a number. I color it using red or blue. I mean to coloring. Now here is an example. This is to coloring of the first 6 positive integers. Now it's clear what's the meaning of the monochromatic one. That means they have the same color. Now here we got a 3-term arithmetic progression here, right?
So are we working mod n or not? Are we allowed to move that around?
That's I'm going to. Okay, now we need to talk about what's the meaning of the cyclical group of Zm. Think about this. In our group, in this system, we have only n numbers 1 through n with the bar over there. That's called representatives. Now the thing is, how do we do the plus? Right? We do the plus like this. Give me I and j. We plus I and j normally. If the sign is less than n, that's what we got. And put a bar over there. Give me a second, okay? Yes.
N is not 0 here?
N is not 0.
Okay.
If I plus j normally is a sign bigger than n, then we take the remainder, and that's what I got. Take an example. If we consider Z7, now we do the plus 1 and 5, and 1 and 4 like this. Since 1 plus 4 is 5. 5 is less than 7, so we just put a bar there. In this case, 3 plus 5 normally is 8. Here we take the remainder is 1. That's how do we do the plus here. Okay, next thing is what's the meaning of the arithmetic progressions in Zm? Now we put the numbers clockwise on a cycle, and then given A and D, we start from A and we work D steps clockwise. Now here is example. Now this is Z7, right? We start from 2, and we walk clockwise by 2 steps. We got a second term, third term, fourth term. This is a 4-term arithmetic progression in Z7. Is that okay? On this kind of thing, we have a very, very classic theorem that's called the Van der Waals theorem. The statement of this theorem is this. For any given possible integers k, there is some positive integer n, such that if we coloring the first n positive integers in any way, there is at least one monochromatic k-term APs. Now the least such n is called the van der Waals number. We use W of k here. The first thing is when the W of 3 equals 8, that means no matter how do you to color in the first 8 integers, we can find out a monochromatic 3-term AP.
W of 3 is 9, not 8.
Is 9?
It's 9.
Okay, I'm
For
sorry.
8, you can have this carry about 3 term.
Yeah, it is.
And one more.
Okay, I'm sorry for that. That's 9. So, for example, this is if you put something here, then you got a monochromatic one is 2, 5, and 8, right? All right. Let's start with this kind of question. In 1999, Goran proposed the following $100 problem. That means if you can solve this problem, you will get a $100 check. This is Goran put this kind of question is in the conference in Memorize of Paul Eldridge. The question is this: if we let V of n is the minimum number of monochromatic 3-term arithmetic progressions in any two coloring of the first n integers, given we know the number should be some numbers times n and plus the middle term, we want to determine the coefficient beta. Okay, now here is some observation. If we color the first n integers equally likely, that means give you a number with the same probability, the color is red and or blue. That's what I mean coloring equally likely. Then you can say for each 3 AP has a probability 1/4 to be monochromatic. Now the total number of 3 APs in the first n integers is this. This may be a good exercise. So if we color that randomly, then we got beta is 1/16. And people believe that's right. That's common belief, that's right. The first result on this question is this. In 2008, Parallel and his two co-authors showed this. Here, for this fraction, you may not know how large it is. This acid, the upper bound is less than 1/16. That means what's commonly believed is wrong. That means the beta should be less than 1/16. Equivalently, there is some two coloring giving a fewer number of monochromatic 3-term APs than the coloring, than the random coloring. In this paper, they did show how do we do the coloring. Okay, now let's consider Goran's question on the cyclic group. Now here we have n square in k-term AP since you have n choice for A and n choice for D. Let's say you two coloring, and then we use this notation to be the normalized number of monochromatic KP induced by C. That means, given this two coloring C, let's count how many monochromatic KP do I have, and then we divide it by the total number, n squared. That's what I mean the normalized number. And if we drop the coloring C, that's the minimum number among all colorings. We're going to talk some results we are known. The first result about this is when the n is prime number and the k is 3. So that curves is k show this. If this A and B is a two coloring equivalent is equivalent to C, that's a partition. And one coloring class has this many numbers, then the normalized number is exactly this. So that means when n is prime, then the number of 3-term monochromatic APs depends on the size of the coloring classes. We observe that this is reach the minimum value 1/4 when alpha equals 1/2. This is a calculus course, maybe you can find out. It's easy. That means M3n, that's 1/4. Another way to view this result is this. If you random color in the first the number, sorry. If you random coloring, then we achieve the minimum number. Okay, now a natural question is this. Since here we assume n is prime, what can we show if n is general n is not necessary to the prime number? So we have this kind of theorem. So for general n, we can prove this. So for any integer, if n is large enough, and given any two coloring of Zn, then it contains at least this many monochromatic 3-term APs. In other words, we have this. That's to say, random colorings also gives you the minimum number of monochromatic 3 APs. Okay, next question is this. This is for the 3-term AP. Now, what can I show? What can I say for the 4-term AP? Okay, we also start from prime number. This is a very easy observation. The random coloring gives this. And Gauss in 2007 proved that this number is strictly away from 1/8. And for the lower bound, the Cameron and his two authors in 2007 proved that this number should be at least this much. I didn't mention here the Gauss result using the harmonic analysis and a probabilistic method is pretty complicated. It's not that easy to understand to read the paper. For the Cameron, for this result, I need to mention here their results actually hold for any abelian group of other n if the order is the GCD of n and 6 is 1. That means you to coloring any abelian group, you can still talk about the 4-term AP. Based on these results, Wolf in 2010 proved this kind of result. She proved, she proved the R-bound in this. You can say this is, 8 times this is more than 1 million, right? It's very tiny. And the next part is the lower bound. She can show this is at least 1/16. All right. For the lower bound, we can show this for the general n. N is not necessary to be the prime number. We can prove if n is not divisible by 4, then we can show the lower bound is at least this much. But when n is divisible by 4, we get stuck here. We cannot improve the previous result. So here if we compare 7/96 is between this interval. That means roughly we improve the lower bound from 1/16 to 1/14. So this is the natural corollary. If n is prime, then we have this lower bound. Okay, this is for the R bound. R bound is case-wisely. If 20 divided by n if n is divisible by 20, we can show this. And if n is divisible by 22, we can show this. If n is odd, this equal 2 is not a factor of n. That's to say n is odd. Then we can show this. Now, last part is n is even, but n is not divisible by 22 nor 20, then we can show this. All right, a natural corollary is for the prime number p. We can show that. We just take this part. Here we got a remark. You can see how the improvement we got here. So this is what I got the R bound. All right, this is for the R bound. If we use the same idea, we can show some R bound under 5-term APs. That's the following theorem. The random coloring given this, you can see this is strictly all the way down from here. But the point in this, there's no result of significance about the level and 5 and the 5 APs. It seems the level bound of the 5-term AP is more challenging. All right, let's introduce some notations. This is C is coloring, and this is A is a set of the red elements, and then B is a set of the blue elements. And we'll see the size of A is alpha times M. And then AI is a set of our KAP whose ith number is red. Since we give some orientation for the KAP, so we can talk about what's the ith number. We have this kind of thing. The size of the AI is alpha times n. Since here we have alpha n choice for the initial term and n choice for the common difference. And the same thing for the BI. For the level bound, that depends on this kind of lemma. For any ij, if the GCD of j minus I and n is 1, then we have this. Actually, this means the set of the number of k-term APs such that the ith number and the jth number are red, right? That's what I mean with this. So we can clearly state what the size of that set is this. Now, if the GCD of these two is not 1, then we have this. So our level bound depends on this lemma. All right, now let's recall this R bound. I will give you some idea about how do we show the R bound. Our R bound is constructive, and that will tell you explicitly what the coloring is. All right, given n and some positive integer n and q is less than n, that we write n equals k times q plus r. Here r is some positive integer between 1 and q minus 1. Then first we find a good two coloring of ZQ. And then we put k copies of the ZQ with the same coloring clockwise. Then we are left to coloring the remaining R numbers, right? So we're coloring the remaining R numbers in Zn arbitrarily. And we use C to denote this kind of two coloring. We observe that the monochromatic KPs, we have two parts. The first part is this. That AP contains no number from the last R numbers, right? That's one part. The other part is the KP does contain some numbers of the last R number. The point in this, for the second part, the normalized number is little 1. We don't care about that. All right, for this coloring, we have 8 types of APs. So we use 0 to 8 to 7 to denote the type. And we say AP is of type I, the meaning is this. We write I as a 3-digit binary number. If for j between 1 and 3, if the jth digit is 1, then we have this kind of thing. Here is an example. Now, if we write a 6 as a binary number, in this, right? Think about this. This is the n, right? This is the last n integers here. Now we start from some number a. Since the first digit of 1 is 1, right? So that means the second number should cross that part. So we get here. The second digit is also 1. That means we need to cross it again. So we get here. The last digit is 0. So we don't cross. But here. So this was the meaning of their types. Alright, this is what's the meaning of their each type in Zn. And this was the meaning of the corresponding meaning in their ZQ, the small integer. Alright, now if the density of each type, if we don't talk about the coloring among all 4 APs in Zn is AI, and the fixed type, let A and D run over all numbers in ZQ, and we got BI monochromatic KAP in Z. Oh, sorry, this should be in ZQ. Then we have this kind of thing. We can exactly compute what the number it is. This is how do we show the show the outbound. Okay, next I want to show you what the coloring is. Now, when 20 is divided by, when n is divisible by 20, then we first coloring Z20 like this, then we put some copies of Z20 and use the result. You can see we can compute the number of the monochromatic one. If n is divisible by 222, then the coloring the Z22 is this. You can observe for each of the two coloring, we have the same number of zeros and the same number of ones. That means for each coloring, the red one and the blue one have the same cardinality. Intuitively, that gives you a good two coloring. That gives you a very few number of monochromatic one. All right, for the 5 AP, the coloring is this. We write n equals 74 s plus r, and the coloring of the Z74 is this. We find out this coloring using the computer. Of course, you cannot use your hand. All right. As a corollary, we can use our construction to give an outbound on this kind of thing. If you to coloring the first n integers, and we talk about the monochromatic for turn AP, we can show this outbound. We use the coloring of the Z20. We do come up with an algorithm to compute the number of monochromatic for AP. All right, let's do a summary. Here we have 3 kind of problems. The first one is if we to coloring the Zn, the cyclical group Zn, then for the 3 term we know this, right? For the 4 term we know this. Now there's a still gap between upbound and lower bound. For 5 AP we just know the upbound, but we don't know what's the lower bound. You may find a trivial lower bound using the van der Waals theory, but that number is very, very tiny. We call that trivial lower bound. This is for the Zn. Now the second thing for the ZPP is some prime number. This is what we already know. 3 term, that's completely solved. 4 term, still gap here. 5 term, lower bound is still in question. Non-trivial, we want to find some non-trivial lower bound. All right, last part is if we to coloring the first n integers, we talk about the AP. Then for the 3 AP, we have this result. This result is still gap here. 4 AP, we can show the lower bound. We can show the upbound. lower bound is still don't know. Yeah. In this kind of question, the challenging part now is the lower bound. We do need some clever idea to find out some non-trivial lower bound. Yeah. I think that's.
Any questions for our speaker? I have one.
Yeah.
So is there something inherently special about 20 and 22, or are those just numbers?
Oh, the thing is, for 20 days, since when we prove the R bound, right? When n is divisible by 4, our method fails. In this kind of situation, it suggests when n is divisible by 4, it's probably the final good coloring gives you very few monochromatic 3-4 turn APs, so we try we do, we succeed.
So 20 is just
it's coming from that. Yeah, we need to find out some number which is a multiple of 4. Yeah, that's.
It is a computer program to search all the numbers which is small enough. And it turns out 20 and
20 is the best. Yeah.
For Carolina. And for for 5 term APs, then 74 is the best.
Huh.
It's very strange things. Yeah. Sometimes you try small number, try bigger number, you get more. You cannot get better, coverage.
Huh. Yeah, so there's no expectation of the thing that 20 does that makes it the best?
No.
It comes by chance, actually.
Other questions first?